Hello everyone, my name is Menyhert. I'm a fourth year chemistry student graduating this spring of 2021. This video was made possible through the Student Active Learning Initiative, sponsored by the William G. Lowry Department of Chemical and Biomolecular Engineering. In this video, I'll be giving an introduction to VLE phase diagrams. I'll only be giving an overview of these topics as you'll receive more extensive lectures in class. On this slide, I have a general outline of what I will be covering throughout this presentation. First, we'll start off with the definition of VLE, and then move into the two graphical representations of this equilibrium phenomenon, the TXY and PXY diagrams. After an introduction of each of these two diagrams, I'll give a quick comparison between the two and briefly describe when to use each. After this comparison, we'll cover a brief example problem and look at how VLE is used not only in the CBE 2200 class, but also the general CBE curriculum in your possible future career. Finally, I'll end this presentation with just the lightest overview of how this topic can be extended to more difficult solutions and some extremely non-ideal solutions. So, what is VLE? VLE is an acronym for vapor-liquid equilibrium. Basically, it is used to describe both the evaporation and condensation of a mixture of components. It not only describes the point at which these components will be fully evaporated or condensed, but it does this for all mole fractions of mixture between two components. We will only be assessing two component mixtures in this presentation, as they are what is discussed in CBE 2200. In the future courses, you will extend these principles to mixtures and more components by using tertiary phase diagrams. In our class, understanding binary mixtures can be done through equations or through graphical means. This PowerPoint will address the graphical side of VLE, and these will be referred to as VLE phase diagrams. You can see an example of this diagram on the right side of the slide. Now, when looking at these charts, there are two types that correspond to the two variables that affect the evaporation of mixtures. These two variables are temperature and pressure, and therefore have corresponding TXY and PXY diagrams. TXY diagrams are for constant pressure, and PXY diagrams are for constant temperature. Each of these diagrams have use that depends on the constraints placed on your system. Usually, however, you'll only be provided one of the two charts and be asked questions related to that chart only. So on this slide, we'll start the breakdown of a TXY diagram. Upon examining the axis, we'll see temperature versus mole fraction. This mole fraction can be described as either X or Y, and therefore when using the naming convention Y-axis versus X-axis, we arrive at a name TXY. Knowing that this is a TXY diagram, we know that pressure has to be held constant, and that can be seen at the top of the chart in the title at 1.01 bar. Next, we can look at the two components of this graph, toluene and benzene. I chose toluene and benzene for this graph because when these two components are in a mixture together, they behave ideally. When we look at the x-axis, we see only the toluene mole fraction is represented. However, since we know that it is a binary solution, benzene mole fraction is just 1 minus the x-axis value. And it should have just popped up on your screen for the benzene mole fraction. Since we know both where the toluene and benzene mole fractions are equal to 1, it would simply make sense that at these points, we would find the corresponding boiling points of each of these pure components. So at the extremes of the graph, you should be able to see that I've marked them for the benzene and the toluene components. From a primary glance, we can already see that these diagrams are chock full of information that can help us in describing the VLE phenomenon. On this next slide, we're going to start to develop the 5 different regions shown on the TXY graph. These 5 regions are the subcooled liquid, the bubble point, the VLE region, the dew point, and the superheated vapor region. Let's assign these regions in order, starting with the subcooled liquid point. A liquid or solution is considered subcooled when it is below its boiling or bubble point. Therefore, we are looking for a region that is below these points on the graph. We can then assign this region to the bottom right of the graph. The subcooled liquid region is here because this is the lowest temperature area of the chart and is the only region below the bubble point or boiling point of the mixture. Next, the bubble point is where the first bubble of gas would appear in the mixture if heated from a subcooled state. Another explanation of this is where evaporation would first start in a heated solution. Knowing this, the bubble point must be the next closest region to the subcooled liquid region. We can define this whole red line as the bubble point for this mixture at each different composition. This means that at a 0.1 toluene mole fraction, the first bubble would form at 82 degrees, while at a 0.7 toluene mole fraction, the first bubble would form at 98 degrees. The next region of interest is the VLE region. This is a range of temperatures at each composition in which a vapor-liquid equilibrium exists. For pure components, this area would simply be a line where the VLE region would equal the bubble point region, which would also equal the next area of focus, the dew point region. An example problem concerning how you can identify the composition of the gas that is being produced in the resultant liquid will be brought up later and hopefully clarify this region. The second to last part that we have to address is the dew point. The dew point is the point at which, if a completely gaseous mixture was cooled, the first drop of liquid would appear. As with the bubble point, this point occurs along the whole top blue line. The final region is the region in which the gas is heated above the dew point, also known as the superheated vapor region. You can see this area at the highest temperature region of the gas, because at the higher temperatures, it would just be heating a gas more and more, and therefore it stays in the superheated vapor region. Now we'll look at PXY diagrams. Similarly to the TXY diagrams, on the x-axis we have the toluene mole fraction and inversely the benzene mole fraction. The major difference starts when we look at the y-axis. As you can see on this chart, the y-axis represents pressure. Knowing this, the temperature must be held constant, and you can see this to be true as shown by the graph title, shown at 25 degrees Celsius. When we are able to see the boiling point of the pure components at the extremes of the TXY chart, the PXY shows analogous information. On this chart, the extremes show the pressure at which the pure component boils at a constant temperature, also known as the pure component's vapor pressure. Thankfully, the PXY diagram has the same 5 regions as we saw in the TXY diagram. However, they're slightly different. I'm going to assign them right now. As you can see by the labels, the regions seem to be flipped as compared to the TXY diagram. If we take a step back and think about this logically, this makes sense. At a constant temperature, if you increase the pressure of a gas, it condenses and becomes a liquid. This same phenomenon is seen in the chart. If you choose any point and move vertically up the y-axis, you can see the vapor changes to the VLE region and then to a liquid. Now for a quick slide of comparison. We have the TXY and PXY diagrams shown in each of the regions labeled. Here you can see directly that the regions are flipped. Pretty obviously, as previously discussed, you apply the TXY diagram to systems with constant pressure and PXY diagram to systems with constant temperature. Now we're going to move into an example problem using the benzene-toluene graphs we just saw. The problem reads, in our benzene-toluene system, please answer the following questions. What is the boiling point of toluene? What is the boiling point of benzene? If a mixture has a 0.7 mole fraction of toluene and is at 109 degrees Celsius, what region is it in? And finally, if a mixture has a 0.6 mole fraction of toluene and is heated to 98 degrees Celsius, what is the composition of both the gas and liquid phases? To start this problem, let's start with A and B as they were addressed on an earlier slide. We know the boiling points are the extreme of the graph, and therefore we can read them directly off the chart. So you can see I read them as closely as I could, and I put an about value for the temperatures that I saw fit. Next, we want to identify part C of the question. If a mixture has a 0.7 mole fraction of toluene and is at 109 degrees, what region is it in? Let's first plot this point. We can identify what the region is either by memorization or common sense. Common sense tells us that at higher temperatures and constant pressure, you will be heating a vapor, so it will be a superheated vapor. Memorization says that the region is the highest region in the TXY chart means it is a superheated vapor. Therefore, since both of these agree, we can easily conclude that this point is in the superheated vapor region. Now for the final part of this question. If a mixture has a 0.6 mole fraction of toluene and is heated to 98 degrees Celsius, what is the composition of both the gas and liquid phase? To answer this, we will solely use the chart. First, let us plot the 0.6 mole fraction and assume it was instantly heated without any evaporation to 98 degrees Celsius. Then, for these types of problems, to understand the composition of the gas and liquid phases, we draw a line parallel to the x-axis that intersects the bubble and dew point lines. Then, we draw vertical lines to connect the intersections of the bubble and dew point lines respectively to the x-axis. From here, we can read off the values for the liquid phase and the vapor phase. The vertical line that originates from the dew point line is the composition of the vapor phase. Similarly, the line that originates from the bubble point line is the composition of the liquid phase. You can see the values that I determined for these compositions to be here on the right. Your values may fluctuate slightly due to how you draw your lines, and this is okay. There are usually tolerances on these problems, so you could have slightly different values and still get full credit. Now, I want to identify the usefulness of this diagram throughout your college career as well as your future career. In 2200, this diagram helps by bypassing the use of multiple VLE equations. It really helps expedite the process as well as laying the groundwork for future classes. Also, these diagrams allow you to use real-world data for binary mixtures. In future courses, you can easily expect these diagrams to pop up in separations, unit ops, and OChem. For separations, VLE diagrams is a covered topic, as well as being the basis of distillation. Similarly, in unit ops, a strong understanding of VLE helps distillation techniques. Finally, for OChem, this helps as I personally had some quiz problems during the lab portion of this course that dealt with VLE diagrams, as well as the course requires simple distillation techniques. In your career, VLE could also be useful. My second year, I had a co-op opportunity with Cooper Tires as a materials application research intern. During this opportunity, I had many lab duties, but VLE was directly responsible for a solvent reclamation process that I had to optimize. It turned out to basically be a fractional distillation problem that I had to solve, but the basic understanding of VLE helped me greatly. This can be applied to other fields, such as the fuel industry. To separate out the usable components, such as gasoline from crude oil, distillation techniques are used, and therefore this is based around an understanding of VLE. For the final slide of this presentation, I wanted to address the fact that I have mostly only presented ideal solutions. In the future, some solutions that are less ideal, such as ethanol and water, can be seen that can create problems. An image of this VLE diagram can be seen in the bottom left of this slide. This can be made even worse, especially in distillation with the introduction of azeotropes, such as the azeotropes shown in the graph on the bottom right. I wanted to introduce these topics so that you could keep them in the back of your mind so that you felt more familiar when they're introduced in the future. Okay, everyone, I hope that you all learned something and found this video useful. Thanks.